I also want to express my appreciation to the organizers for organizing such a thoughtful event to honor Vera Rubin, and also to the other participants. I didn't have an opportunity to meet Vera Rubin, but I'm really grateful for all of your personal stories. So today it's my pleasure to talk about dark stars, which is a phase of stellar evolution during which dark matter may have actually powered the stars. So I'm going to start with this huge picture. The period that is really relevant here is actually the Dark Ages. So this is after recombination, where the photons can stream through the neutral gas. And basically it's at this time when the gas and the baryonic gas and the dark matter are clumping together to start to form structures. And eventually, after about 180 million years, the first stars can form out of the gas. So what did they look like? These stars are called Population 3.1, and what distinguishes Population 3.1 stars is that the abundances of elements in them come strictly from Big Bang nucleosynthesis. So that's one aspect of it, and the other is that they're completely unaffected by any other astrophysical sources. So unlike subsequent generations of stars, which may have been affected by the radiation from the first stars. So these guys formed in dark matter mini-halos at very high redshift, so redshifts greater than 20 probably, and they could form when the first cooling mechanism became accessible. So the first cooling mechanism was molecular hydrogen cooling. And if we want to think about when that happened or what the criterion was for that to happen, the fraction of molecular hydrogen is related to the temperature. So you can write a relationship between the mass of a halo and the redshift at which this temperature is reached. So this is the minimum halo mass for star formation to begin, and this is just one parameterization, but it just illustrates the point. Okay, so what did they look like? They were predicted to be very massive. From the theory side, basically there was insufficient cooling for them to become larger, but simulations also show that the typical masses are more than 100 solar masses. So let's talk about their formation, evolution, and signals. Okay, so the idea here is that we begin with mini-halos in the early universe, and these dark matter mini-halos, well, they have about 85% dark matter and 15% of those BBN abundances of stuff, so mostly hydrogen and helium. When molecular hydrogen cooling becomes possible, the gas can then collapse, and so this gas is collapsing in a very dark matter-rich environment. And eventually, as the gas cools and collapses, the dark matter, that creates a very deep potential well in the center, and so the dark matter is dragged into the potential well as well. So at this point, there is a thing that could happen, which is called the dark star phase. And so this is the period where dark matter heating could power the star. So this was an idea by Doug Spoliar, Katie Fries, and Paolo Gondolo from 2008. And most of my talk is going to be focused on the consequences of that. So during this period of the dark star phase, baryon accretion will continue. Eventually, the dark matter fuel may be used up, and so then what you would end up with is these very large stars that could end their lives by collapsing to black holes. Okay, so that's sort of the formation of and evolution of individual stars. But there is dark matter all around them, right? And so when a compact object forms at the center of a mini-halo, the dark matter is going to be dragged in and create something called a dark matter spike. Those compact objects plus dark matter spikes will evolve in the universe. And so, as I'll talk about later, we are able to determine the local distribution, which helps us figure out what the consequences are for observing these things. So then we can talk about direct and indirect signals. So this could be direct observation, for example, with the James Webb Space Telescope. We could be thinking about looking for diffuse or cosmological signals. So if you think about all of the dark stars or their remnants and the dark matter spikes in the universe, or we could think about looking for these guys in our galaxy, so in and around the Milky Way. And they could show up as point sources if they're bright enough, or they could contribute, for example, to the diffuse gamma ray flux if they're faint and you're thinking about the contribution from all of them around in the Milky Way halo. Okay, so what is a dark star? So if we're talking about the dark star phase, we should think about when these objects were forming. And basically, the picture that you should have is this baryonic object forming in the center of a dark matter mini-halo, right? So it's forming, basically, if dark matter annihilates, then you have that the annihilation rate is enhanced by the density squared. So if there's a place with very high density, you're going to get a large dark matter annihilation rate. The POP 3.1 stars formed at high redshift, we already said, so you get an enhancement in the dark matter density because of the high redshift. And they also, because they're population 3.1 stars, tend to form at the center of the mini-halo, where the dark matter density is really the highest. Okay, so the question is, could dark matter annihilation power the star? That means, could the annihilation products, the standard model particles that are produced in the annihilations, get stuck in the star and sustain it from collapsing, right? The same way that fusion sustains stars. And there were 3 conditions that were identified. So the first is that there has to be a sufficiently high dark matter density for a large annihilation rate. The second is that those annihilation products definitely have to get stuck in the star enough. And the third is that the dark matter heating, in order to be considered a dark star, the dark matter heating has to be the dominant source. So I'm going to go through these one by one. So if we think about the sufficiently high dark matter density, on the previous slide I gave you 3 reasons why these are forming sort of at the right place and the right time. But it turns out that that's not quite enough, but there's something else that happens in these objects that does result in a high enough dark matter density, and that is adiabatic contraction. So anytime that you have a compact object in the center, as I said before, the dark matter is going to get dragged into this deepening potential well. And so this is a picture of what happens. This is the density as a function of radius. The black here is an example NFW profile, and the dashed blue and red lines indicate the adiabatically contracted halo profile. So these 2 are just for 2 different core hydrogen densities. So these are the adiabatically contracted profiles if you start with an NFW-like initial halo profile. And it turns out this is completely robust to whether or not it's NFW. This even happens with a completely cored profile. Just for a comparison, the black dots here are simulation results from Abel, Bryan, and Norman. So we expect adiabatic contraction to happen, and basically whether or not there's a dark star phase, you are going to get a dark matter spike around any massive compact central object. The other thing I want to point out here is that even with adiabatically contracted dark matter halo profiles, you think like, oh, that's a ton of dark matter, but actually the dark matter really only makes up less than 1% of the mass of the dark star during that phase. Okay, so number 2 is the annihilation products get stuck in the star. So if we think about the amount of energy produced in a dark matter annihilation, it's like the annihilation cross-section times the density squared divided by the mass of the dark matter particle. Now, not all of that is necessarily going to get stuck in the star. So if you think about a typical dark matter WIMP particle who annihilates to standard model final states, so pairs of standard model particles, if these things aren't stable, they hadronize, decay, cascade, whatever, and at the end of the day, you end up with things that are going to stick around, like gamma rays, neutrinos, and other standard model particle pairs. Neutrinos are obviously not going to get stuck in the star. So if you think about like the range of WIMP candidates, typically the fraction of energy that gets stuck in the star is around 2/3. Okay, so if you want to calculate the actual heating rate, you have to multiply the energy that you get out of each annihilation times that fraction. And the other thing is, if the cloud is very fluffy, if the cloud of baryons is very fluffy, not all of the annihilation products are going to get stuck either. And so depending on the mass of the dark matter, there's a minimum hydrogen core density at which the dark matter products will get stuck. Okay. So the cool thing here is that this process is extremely efficient. So even though the dark matter makes up a very small fraction of the mass of the dark star, because you get 2/3 of the mass energy converted into that power, and it's happening over a huge volume, not just in the core like nuclear fusion, this is a really efficient process. Okay, so the last thing is that dark matter heating dominates. And so if we, this is a picture of the protostellar evolution. This is in the temperature number density plane. So you can think about a dark star phase protostar following this evolutionary track for 2 different masses of dark matter particles. And basically, if you look at the evolution of this guy, you're watching it until the dark matter heating dominates over other heating and cooling mechanisms. So in this case, it's over the molecular hydrogen cooling. So for 100 GeV WIMPs, when these black dots are reached, that's the point where the dark matter heating is dominant. And that happens when the mass of this protostellar object is only about 0.6 solar masses, and it's really super fluffy, so it's like almost 20 AU across. So this is the beginning of the proto-dark star phase, but that doesn't mean that it's actually a dark star yet. Once dark matter heating dominates, then you still have to wait for it to equilibrate when it becomes a dark star. So once hydrostatic and thermal equilibrium are reached, the dark star phase begins, and then the star really is powered by dark matter annihilation. So here's a picture of the evolution. The luminosity is a function of time. So you start with a protostar that's a very small thing, and it follows this evolutionary track. During the dark star phase, the temperature is about 10 to the 4th Kelvin, and you can see the different contributions to the luminosity here. So during the dark star phase, it's basically entirely powered by dark matter annihilation. In this pretty simplistic picture, once the dark matter fuel is used up, then other heating mechanisms takes over. So it collapses, and then eventually nuclear fusion takes over. And so this is a dark star that would have ended its life as about 180 solar mass fusion powered star. Sorry, 800 solar mass fusion power star. Okay, so that was the simple or the basic picture. So there's a big puffed up star sitting at the center of a mini halo. But the picture is probably a lot more complicated than that. So you could have things like centrophilic particle orbits, so particles that spend most of their time way out in the dark matter halo will pass very near the center and could contribute to the annihilation. And also there could be dark matter capture that's significant. If dark matter scatters on nuclei, then occasionally dark matter will be captured into this object as well, and that could contribute to the reservoir of dark matter that's available too. So these different mechanisms prolong the dark star phase, and they also lead to objects that look pretty different. So this is an HR diagram. The solid and dashed lines, the dashed ones are for a dark star without capture, and the solid ones are for dark stars with capture. And you can see that they have much different temperatures at the end of the day. So they both kind of grow big, but they will look very different. So the dark star phase could be long-lived, and that would result in not only dark stars that look different, but also really supermassive ones. These things could grow to be like 10 to the 6th, 10 to the 7th solar masses. So how do we detect them? So I already mentioned direct observation with JWST is one possibility. And I'm just going to give you one quick picture of what that looks like. So this is the sensitivity of JWST in the 3.56 micron band. This is the magnitude that it's sensitive to as a function of redshift. So this is with an exposure of 10 to the 4th seconds, and this is with an exposure of 10 to the 6th seconds. And the colored tracks are for dark stars of different masses. So everywhere from 10 to the 4th solar masses to 10 to the 7th solar masses, either forming at redshift of 15 or 20. And you can see these are plotted as a function of redshift. So for example, for these largest ones, you would be able to see a 10 to the 6th or 10 to the 7th solar mass dark star with an exposure of 10 to the 4 seconds, really out to their formation redshift. But for the lighter dark stars, if dark stars are a bit smaller, then you would need a longer exposure. That's sort of the basic picture. There are really two other things that will help you see these better. One is the dropout technique, and which will allow you to see objects down to about 10 to the 4th solar masses. And I noticed at least 3 of these people in the audience, so please feel free to ask Katie or Cosmin or Paul, or if anyone else is here, please ask them. The other thing that you can do is you can look at magnification by a foreground cluster. So Zackerson et al. Looked at lighter dark stars, so up to a mass of about 1,000 up to masses of about 1,000 solar masses, and they found that you couldn't see them unless they were magnified by a foreground cluster. Okay, you could also think about diffuse or cosmological signals from all dark stars in the universe. And so what that looks like, there are a number of ways that these things could appear, right? So you could think about the extragalactic background light contribution from the dark star phase, the accumulated flux from dark matter annihilation around all remnant black holes in cosmological history, and that could be in photons or neutrinos. You can think about radio signals. So if dark matter annihilates to charged products, and then there's synchrotron radiation around the remnant black holes in some magnetic field, that would produce a radio signal. Reionization may be affected by a dark star phase. For example, if the dark stars are sustained by dark matter capture, there could be contributions, well, there should be contributions to 21 centimeter signal in terms of what the first stars looked like. These would obviously be altering, a dark star phase would alter the mass function of the first stars, so then they would therefore alter the mass function of the black holes. And you can also think about gravitational waves from dark star or remnant mergers. What I'm going to focus on a bit more are signatures of the remnants of these dark stars in our galaxy. So basically, if you think about what's going to happen to these guys at the end of the life of one of these giant objects, they are going to become black holes with some large fraction of the mass of the initial object. So this is similar to work that was done by Hager and Woosley. They showed that for these really big guys, you get a big black hole out at the end. So those black holes surrounded by dark matter spikes could show up in 2 different ways: as point sources if they're bright enough, and so you could think about looking for gamma ray point sources or potentially neutrino point sources, or they could contribute to the diffuse flux of annihilation products if they're faint. So they could contribute to the diffuse flux of photons or neutrinos or charged leptons or antiprotons. So I'm going to focus on photons here. And so the tool that we're going to use to look at those is the Fermi Gamma Ray Space Telescope. So can we use Fermi-lat data to constrain early star formation or models of dark matter annihilation? So this is the diffuse gamma ray flux, and here is the 1FGL source catalog. That was from several years ago, so now we have an update. So here's the diffuse gamma ray flux on a much larger energy range. And our point source catalog now looks like this. The thing I want to draw your attention to here is that these blue dots are unassociated sources. So they're gamma ray sources that are not associated with sources in any other catalog. Okay, so if we think about dark matter annihilation in an individual spike, the annihilation rate is proportional to the cross-section divided by the mass squared. Here we're going to fix the cross-section for simplicity. And so if I use the annihilation rate then to calculate the intrinsic luminosity, so this is the luminosity at the source, what you find, you can plot the luminosity as a function of mass. As you increase in mass, you lose in luminosity, obviously, because of this. But we did this for several different final states. So the other ingredient to the intrinsic luminosity is that you should sum over the final states for all the things that dark matter annihilates to. We just took 100% annihilation to either W's or BB bar or mu plus mu minus or tau plus tau minus. And so you can see that obviously the quark and gauge boson final states are more luminous than the leptonic final states. But we also looked at several different masses for the remnant here as well. So ultimately, increasing the black hole mass obviously means you have a bigger spike, and so you have a higher luminosity that you expect from these objects. If you increase the WIMP mass, you have fewer WIMPs in each spike, and so you have lower luminosity, and leptonic final states are less luminous. So if we want to predict a signal from the remnants, we need to know how many formed over the course of cosmic history. And so if we think about the number of black hole remnants and spikes in our galaxy, we have to relate that back to the number of stars that ever formed, so the population 3 star formation rate. This is a cartoon picture, as I'll show you in a second. We actually use numerical n-body simulations to figure this out. But we parameterized the end of population 3 star formation. We don't really know when it ends, but we took some guidance from Greif and Brome. And we took 3 different models. So if star formation ended early, so that means that it was only this sort of part of the diagram here. If star formation ended sort of sometime around redshift of 15, or if the first stars ended forming at redshift of 10. Obviously, subsequent generations of stars took over after that. So those are our 3 models. And then we can think about what a dark matter spike looks like in each of those cases. So this is the dark matter density as a function of radius for an individual spike around 100 solar mass black hole. There are a couple features here to point out. One is just that there's this plateau at low radii. So this is the sort of a maximum density that you can have, assuming circular orbits. And then because it would have been depleted by annihilation in the center, essentially. And then you can also see that the profile depends pretty weakly, but it does depend on the redshift of formation. So if it formed in a more dark matter dense environment, then you get a little bit of a boost there. So where do we get our distribution? This is the Via Lactea 2 cosmological n-body simulation. You can see that it has a particle mass of about 4,000 solar masses. And this was the first simulation of the galactic halo that was able to directly resolve the mini halos where first stars would have formed. So we basically use this to track potentially star-forming mini halos from high redshift, and then figure out the distribution today. So if you give a range for the redshift and mini halo mass, this is the distribution of, we call it dark matter spikes as a function of radius today for our early, intermediate, and late termination of star formation models. And then we compared that also to this sort of analytical model from Bertoni, Zentner, and Silk. And this is the total number of spikes in the Milky Way halo that we found in each of these cases. All right, now, did all of these things form population 3.1 stars, dark star phase, remnant black hole? Probably not, and so we had to define this fraction of population 3.1 capable mini halos that actually did host one of these objects. So if you think about the actual number density of spikes, it's this fraction times the total possible. So it's plotted here as the total possible. Now, how are we going to see them? As I said before, they could show up as point sources, or they could show up in the diffuse flux. If you think about them as point sources, they may actually already be some of those unassociated sources in the FGST catalog. So the considerations here are, if they're very bright, the brightest one actually should not be brighter, obviously, than the brightest observed source in the Fermi catalog. That's a pretty hard limit. And so that allows us to find this define a minimal point source distance. And if the source is far enough away, so if it's dim, then the Fermi wouldn't have been able to see it as a point source, and so basically that defines a maximal distance for point sources. So all point sources in the catalog have to be located between the minimal distance and the maximal distance. So you can ask how many point sources are there? Do we predict the right number? Are they somehow related to the unassociated FGST sources? And what can we learn about the number of objects that formed in the early universe from looking at those? And the alternative to that is that if the spikes are dim enough or far enough away, then they won't be identifiable as point sources, and so then they would contribute to the overall background, right? And so you can ask if the expected diffuse flux from all non-point source spikes is consistent with the measured flux. So I'm just going to show you the minimal distance and the maximal distance for point sources. So basically all point sources have to be between here. I'm not going to dwell on this too much, but you can see that in cases where you have a very bright spike, basically the nearest point source would have to be farther away than the galactic center. The alternative to that is you have a very dim spike, in which case they could be very, very near to us. All right, so if we want to constrain this fraction of potential star-forming mini-halos that actually did form a first star, then you can do it with the point source population, and so we require an expectation of less than one spike within this minimal distance of our solar system, d min ps. And with the diffuse flux, basically the flux that you actually get is that fraction times the flux if all of the potential star-forming mini-halos did form them. And so we require that the diffuse flux didn't exceed the measured flux by more than 3 sigma. So here's an example of what these constraints look like. This is the maximum value of that fraction of potential star-forming mini-halos that actually did form them for models where the black holes had a typical mass between 1 solar mass and 10 to the 5th solar mass, between 10 solar masses and 10 to the 5th solar masses, for some different dark matter annihilation scenarios. I'm not going to spend too much time on this because I want to point out some important caveats. Are we really constructing realistic constraints here? So if you think about bright point sources, we did this we assumed that the brightest one couldn't be brighter than the brightest Fermi point source, but actually we know what the brightest Fermi point source is. It's the Vela pulsar. And there's probably not a dark matter spike directly along our line of sight to Vela. And furthermore, there's probably not another one directly along our line of sight to the next brightest Fermi source, right? So it's probably more realistic to require that the brightest spike not be brighter than the brightest unassociated point source. That's like 1/22nd the brightness of Vela. And the other thing is the dynamics of the inner galaxy. And it turns out that this actually doesn't matter that much, but there's a lot of complicated stuff that happens in the inner few kiloparsecs of the galaxy. So it could be affected by dynamical friction or tidal mass loss or whatever. So it's probably prudent to not worry about the real inner galaxy. Turns out that doesn't affect things too much. Okay, so this is if it's not brighter than the brightest unassociated point source. The thing I want to point out here is that for scenarios where you have very bright spikes, the fraction of star-forming mini-halos that could have possibly formed a dark star or a POP 3.1 star is actually very small. So here the constraints go down to about 10 to the minus 4. In other cases, though, if dark matter annihilates to leptonic final states, then the constraints are actually pretty weak. Okay. So summary is, this is an example of how to place limits on the fraction of mini-halos in the early universe that could have hosted the formation of the first stars. If remnant black holes are very massive, then the fraction of early mini-halos that hosted these objects is probably pretty small. If dark matter annihilates to quarks or gauge bosons, and if the typical remnant is a sort of medium-sized black hole that you would expect from POP 3.1 star formation, then there are some constraints on the fraction of early mini-halos that could have hosted a POP 3.1 star. And the smallest guys are not really constrained, but these are probably also not favored to be POP 3.1 remnants anyway. So could one be hiding in the Fermi catalog? It is definitely possible. There are more than 1,000 unassociated sources in 3FGL. So I just want to end by saying a couple words about radio signals. So I've talked a lot about annihilation to final states that directly produce photons, but dark matter annihilation, if it produces charged particles and those charged particles radiate in magnetic fields, then you would also expect some synchrotron radiation signal. So dark matter annihilation in extragalactic structures is a potential explanation for the radio excess observed by Arcade 2. Some challenges that have been pointed out recently is that, like dark matter, annihilating to leptonic final states is really preferred. And the reason being that in order to get the necessary signal, if the mass is very large, then the annihilation cross-section has to be pretty large, and that's in tension with other indirect detection constraints. However, what's different about this situation is that you have very different dark matter clumping than what you would otherwise expect. So this is something that I had an undergraduate student, Matt Stevens, at the University of Utah, working on. These pictures show you basically this is the sky temperature as a function of frequency, and this is the excess. This is the issue right here. This is with some, if you subtract out the CMB, and then if you subtract out some unresolved sources, basically you still have this excess. Just to give you an idea, it's still there. When Matt plotted this, he didn't plot it with a subtraction, so this is the initial, so there would be a little bit of subtraction from this. But this is the synchrotron radiation that you would expect in a model with a fairly large black hole, a magnetic field of 1 microgauss, and the point here is that you can potentially explain the arcade excess, and this should really just be viewed as a demonstration that this type of substructure can get the job done. Okay, so with that, I will summarize. So the first stars may have experienced a phase where they were powered by dark matter annihilation rather than nuclear fusion, and these are what are called dark stars. In some cases, this dark star phase could have lasted a very long time, potentially even until today. They would have been very large and very bright, and each would probably leave a black hole remnant surrounded by a dark matter spike, which could be observed. So dark matter probably, and certainly could have played a critical role in the lives of the very first stars in the universe, and observing these objects would definitely help us understand the nature of dark matter as well as its role in the formation of the first stars. Thank you.
Do we have any questions? Am I right that actually also non-thermal dark matter candidates could source dark stars?
That's right, yeah.
If the annihilation rate is much enough.
Yeah, that's right. So, yeah, absolutely. Anything that annihilates, right, you just have to calculate what fraction of the stuff it annihilates to is going to get stuck in there. So I had a paper with Scott Watson some years ago about non-thermal dark matter, but you're probably thinking about lighter non-thermal dark matter, not heavier.
Depends. How light or heavy was your dark matter?
So with Katie, we looked at like GeV dark matter, 1 GeV to 20 GeV or something. With Scott Watson, I looked at heavier stuff, like up to several TeV.
Okay. Any other questions? I have a question.
Sure.
So dark matter annihilation can power the first stars and be a very significant effect. Has anybody studied the possibility of much more subtle effects on stars, on dark matter annihilation on stars today, given that we've got many more stars?
Yes, there are many effects of dark matter annihilation on the first stars. So from capture and annihilation to produce like a neutrino signal in the sun or the Earth, like that is a thing that can happen. But there are also a lot of subtle heating effects that can happen for like white dwarfs, for example. So there's a huge body of work on that as well.
Good. Okay. Any more questions? Okay, thank you very much.